Hi everyone, my name is Ikansh and today's topic is Brahmagupta's formula. So let's start off with the cyclic quadrilateral. What is it? It's a quadrilateral where all four vertices are on a circle, or as you would say it mathematically, this quadrilateral is inscribed in a circle. Let's say we want to find the area of this quadrilateral, but only by using the side lengths. How do we do this? That's where Brahmagupta's formula comes in. It states that the area is the square root of the product of the semi-perimeter minus each side length. So it looks something like this. In the semi-perimeter is half of the perimeter. And this looks awfully similar to Heron's formula, but in Heron's formula there's only 3 side lengths. So let's just say D is equal to 0. And then if we move that over there, that's basically a triangle. So if we plug that in the formula, we would get area of S minus A, then S minus B, S minus C, and then since D is 0, we just get S. And this here is Heron's formula. So we won't go into a rigorous proof of why these formulas work, but we can do a short explanation. The key is that this quadrilateral is cyclic, which means these angles add up to 180 degrees. And we know this because that's the sum of their arc lengths is the entire circle. And by the same logic, we know these angles also add up to 180 degrees. So now that we have some information about their sides and their angles, we can use the law of cosines on these 4 triangles multiple times and we will get this area. Now let's move on to a practice problem. This is the 2022 AMC 10A problem number 15. I drew a quick diagram, but let's read the question first. Quadrilateral ABCD with side length AB7, BC24, CD20, and DA15 is inscribed in a circle. The area interior to the circle but exterior to the quadrilateral. So let's shade that area in quickly. And we could write this out as the area we want is equal to area of circle minus the area of ABCD. And this can be written in some form, and basically we have to find this area. So the first thing we should notice is that ABCD is a cyclic quadrilateral and we know all of its side lengths. So we can easily compute the area. Let's start off with the semi-perimeter. 7 plus 15 plus 20 plus 24 divided by 2, and we get 33, which means the area is equal to the square root of 33 minus 7, which is 26, then times 9 times 13, and 33 minus 15 is times 18. We can rewrite this by distributing some things. 13 times 2 is 26, then we can just write the 9 out. 13, and then 9 times 2 is equal to 18. And this makes it really easy to take the square root because we can cancel out one term from each product. So we're left with 13 times 9 times 2. And this is equal to 26 times 9, which is 234. So now that we know this is 234, we just need the area of the circle. And that's where a second observation comes in. When we see 7 and 24, we should automatically think of a right triangle with the third side 25. So now let's assume for now this is 90 degrees And we know the opposite angle must sum up to 180 degrees. Which means if ABC is 90 degrees, that means ADC must also be 90 degrees, which forms another right triangle. And we can check if this works. 15 squared plus 20 squared equals 25 squared, and this does work, which means we know both ABC and ADC are right triangles. And if ABC is a right triangle, that means AC must be the diameter. So if the diameter is 25, the radius is 25 over 2, and the area of the circle is just pi r squared. So 625 pi over 4. Okay, let's go back to the area. So now we just know it's 625 pi over 4, the area of the circle, minus the area of the quadrilateral. So this is our area, and now we just need to convert it into their form. 625 pi minus 234 times 4 divided by 4. And this is equal to 936. So if we sum up these values, it's 940 plus 625, and we get 1565, or option choice D. And we're done.